I want to briefly talk about what makes a strong acid and acidity of salt real quick. So strong acids have to do with, I guess, three major factors. Strong acids will have basically a very polar H molecule bond, some sort of really polar bond. Will have weak bond, a weak HX bond. We want a really polar molecule to remove the electron density from this. We need a weak of this, but then we also, the last thing that's going to really help is resonance. Resonance, the ability to stabilization after the fact, stabilization of the negative. These are what make certain things like nitrate and sulfate and phosphate acids. Because, for example, SO4, SO4, if I draw it like this is H2SO4 right here. When we break this off, you have this structure. Now, by itself, that's maybe not the best thing. That may not the best thing, but the fact that I can then shift that, this double bond can shift down to here, or that double bond can shift down to there, and so we can draw several other resonance structures, helps spread the charge around, so suddenly it is not as destabilized. And this is what makes this guy a strong acid as opposed to a weak acid. These resonance structures. Losing the other guy would allow some more resonance structures. That's what explains why HClO4 and HClO3 are strong acids, but HClO2, that's a weak acid. And HClO1 is weaker still. Very weak. Because you don't have as many resonance structures. This one, HClO, we have ClOH. There's no resonance structures really there. This guy, you would have ClOOH. There's maybe one resonance structure. This guy's going to have ClOOH. There's two other resonance structures. HClO4, you have a total of 4 different possible structures once you lose that proton. So the acidity of this goes way up in comparison to the acidity of this. All this is brought about by resonance structures. That's the reason why acetic acid, despite being organic in nature, acetic acid has this structure, CH3, C double bond O, OH. If I put this as ethanol, ethanol is not really an acid. Ethanol is an alcohol. It has certain properties. In a strong enough base, it will be an acid, but most of the time it is not. Ethanol is not an acid in water. Acetic acid is. It's a weak acid, but it is, because when it loses that proton, it is allowed to resonate between the two structures. We're allowed to move that charge around and make that double bond. Switch those double bonds. Now, when it comes to looking at the acidity and basicity of salts, how do you go about doing that? How do you go about looking at the acidity and basicity of salt? So if I have something, I would say cation anion, some sort of cation anion. what you have to do is you break it down into the cation-anion pair and think about your salts. Think about your salts. If the cation, if you put an OH there and you put the cation there, if this ends up being one of the 6 strong bases, then NaOH, LiOH, let's see, KOH, like RBOH, CSOH, and I think you might consider barium dihydroxide and strontium. If it's really any of these guys, if it's any of these cations, then it would be considered neutral. Because the cation, basically what you're looking at, if this is your possible reaction, Na plus and OH minus, what is the likelihood of a strong base going backwards? It'd be 0. It'd be like essentially 0. You're essentially looking at what is the possibility of this guy going backwards to NaOH and H plus. It's not going to happen. It's not going to happen. The same thing with the anion. If the anion is, like, say, nitrate. So if it comes from any of these strong acids, nitrate, chloride, bromide, iodide, perchlorate, chlorate. I mean, those are the big ones you have to worry about. If it's any of those guys, if it's any of these anions, the same thing's going to happen. If I talked about HNO3 and OH minus, what is the likelihood of NO3 minus going backwards and attacking water and going backwards to this? It's going to be 0 or close to 0. So when you look at a salt, the cation is going to control, the cation is going to control basicity. Well, actually, no. The cation is going to control acidity. The cation is going to control acidity, and the anion is going to control basicity. Basically, if I put a weak acid conjugate right there, if I have a weak acid, what's it going to do? A weak acid is going to donate a proton. So if I put ammonium chloride, what would you expect ammonium chloride to do? Ammonium chloride is going to be NH4 and Cl minus. Well, Cl minus is right here. So this guy's a neutral. Now, NH4, not any of these guys. So what reaction would you imagine NH4 doing? NH4 plus water goes to NH3 and hydronium. That's the reaction that's going to happen. Even if it's not one you really expect. If I said iron chloride, ions can act, iron as an element can act as an acid, and it forms iron like hexaaqua, which then can then go to iron aqua hydroxo. So like, and an acid. Or the same thing with zinc. Zinc can do that as well. So transition metals, they're not these groups, so they can act as an acid. Any of our anions, you mix a basic anion. I mix, say, let's say sodium cyanide. Sodium cyanide, a real easy one. It splits up into Na plus and Cn minus. Cn minus is the conjugate base of the weak acid, hydrocyanic acid. So we put that, if you put that in water, what it's going to do? Cn minus plus water is going to form HCN and OH minus. So all those can be controlled. If you look at the anions or the cations, you can predict whether it's acidic or basic. You just look for, is it going to have effect? You have to look at where are these guys related to the strong acids or strong bases. Now there's one other possibility where they're both weak, and then you would have to actually compare the size. And that's kind of a little hard. You have to compare, is the Ka bigger than the Kb? And the bigger value would be the stronger effect, I think. Well, and there's one other thing to note is that Lewis acids. There's also some Lewis acids we can deal with that you don't maybe expect. BH3. Lewis acids are electron pair acceptors, and a Lewis donor, a Lewis base, is E pair donor. So everything that was a Lewis Bronsted-Lowry base is still a Lewis base. The only difference is now we've increased the amount of acids and bases we can have. And we can talk about reactions that don't involve protons. So BH3, what do we know about BH3? BH3, when you draw that, has 6 electrons. It is not happy. It wants an octet. Cyanide, you draw this structure, you have CN, lone pair. What's going to happen? This guy's going to come and boom, attack there. Just the same way you could draw this as an OH. OH, you have a lone pair that can attack this, or say a hydrogen. Proton wants a lone pair. OH wants to give it a lone pair. BH3 wants a lone pair. Cyanide wants to give it a lone pair. And that's the basics of Lewis acid-based chemistry.